Now we're going to take a look at some bigger c values and see why they shift to the right that many units. So first of all, let's look at f of x equals x minus 5 squared. We're going to take our c value and make it negative 5, and we're going to see that it actually shifts the opposite 5 units to the right from the parent graph, x minus 5 squared. Let's take a look at x cubed. And we don't have to exactly do everything exactly the same. Let's take x cubed and shift it 6 units to the right. When we make c equal negative 6, x cubed shifts 6 units to the right from the original. That goes for any point too, not just these certain critical points. Let's do absolute value. Let's make c equal to negative 8. We can see that the transform graph shifts 8 units to the right from the parent graph when c is negative 8. So we want to do a proof as to why this is happening, and that's what we're going to do now. We've already done for x minus 2. In general, we're going to do it for x minus c. So make sure you watch that video first. So again, we want our inputs to be the same. So we want the x values for our transform function to be the same x values as our parent. That will ensure that it's the same y value. And we want to find a value for x2 such that p of x1 is equal to f of x2. So guess what? We're going to set these inputs equal to each other so that when x1 is equal to x2 minus xc, that x2 minus c, that will ensure that we get the same parent y value back. So set x1 equal to x2 minus c, and again you can visually algebraically see in order to get x2 by itself we have to add c to both sides. We have to cancel out that minus c. Therefore it shows that x1 plus c will give us x2. In other words, if we take the original x values, say negative 2, negative 1, 0, 1, 2, and we add c to them, well, that will give us our new x2 values. Let's take, for example, the absolute value function. Our original x values for negative 2, negative 1, 0, 1, 2. In order to get the same exact y values, since this is minus 8, we have to add 8 to all these x values. So, for example, our first one, negative 2 plus 8, would be 6. It gives us the same y value, and then so on and so forth. 6, 7, 8, 9, and 10 would be our new x values. So add 8 if it's minus 8 in the original. Again, it's counterintuitive, but this is why I'm explaining it to you. Let's prove why this is true. So when x1 plus c is equal to x2 and p of x minus c is equal to f of x, then we can do a simple substitution. Since x2 is equal to x1 plus c, we can replace it in our formula here, and then the plus c minus c is going to cancel, and we get what? P of x1 is equal to f of x2 as required, which is what we were originally trying to prove. In other words, the y values for our original x values, negative 2, negative 1, 0, 1, 2, are going to be the same y values as when we plug in our new x values when we make x1 plus c equal to x2, when we add c to our original x values to get our new x values. Pretty crazy. In general, this is what our general chart for our parent function is going to look like, negative 2, negative 1, 0, 1, 2, with their corresponding p values or y values. All we're going to do is add c to our original x values. Now we don't know what c is. It could be plus 5, it could be plus 7, whatever. We just know that that's going to give us our same p values. And again, that's for when it's p of x minus c. We end up adding c to original x values. Again, I know it's counterintuitive, but this is the reason I'm explaining it. And, that might be a good way for you to remember it. Just do the opposite of what's in here to your original x values, and you're good to go. This is what our final chart will look like for our generic p of x minus c function, giving us our new transformed function. We'll be adding c to the original x values and keeping the same parent function y values. Okay, so what does this tell us? When f of x is equal to p of x minus c, so for example, the square root of x minus 4 or whatever, x minus 5 quantity squared, then the parent graph p of x will shift c units, positive c units, to reach the transform graph f of x while keeping the same y values. Therefore, the horizontal shift will be plus c, and p of x will move c units to the right to reach f of x. So, when it's p of x minus c, when it's, for example, square root of x minus 4, it will shift plus 4 to the right. And that's going to do it for this video of horizontal shifts to the right. Whenever you have minus c, it will shift to the right, like in this case, 8 units to the right. If you have any other questions about this, let me know.